Think of something blessed and anything will do.
Hi guys, my name is Steven and I'd like to welcome you back to my calibration channel. I've also brought in two subject matter experts to help me on this topic. That's Carl and Maddie. One of them's really good on frequentist analysis, the other's really good on Bayesian analysis, but I've lost track of which one's which. Anyway, they're here to help me, and I need a lot of help because this is a tough topic. The first thing to note when we talk about Bayesian versus frequentist analysis in the GUM is that the GUM itself is a technical compromise wrapped up in a commercial treaty. So it's never going to be perfect. Also, the GUM is built from the ground up using both of these approaches. So we're not going to be able to reach into the document and repair it by removing one or the other of these two approaches. It's just simply not going to happen. The second thing that's really difficult about this topic is that if you adhere to one or the other of these two approaches, it's quite common to see people turning this into a political battle. So you'll see adherents of one or the other saying, he's a Bayesian, he's an idiot. If you follow him, you're an idiot too. And by the way, the world's going to end if we don't stick to my approach. It's not at all helpful when you're trying to figure out what's the deal here. The third problem is the GUM is a moving target. It's over 25 years old, so it makes a lot of sense that over that period of time, our ideas about how to do statistical inference have changed quite a bit. That makes it even less likely that we're going to be able to reach back in time and fix this document. We have to live with it the way it is. Now, there are some things we can do to remove a little bit of the confusion right away. One thing is that Thomas Bayes died in 1762, and it was only 2 years after his death that his paper on this topic was first published. It was 60 years after that that Simon Laplace decided he wanted to work in the same general area and took Bayesian ideas a whole lot further than Bayes ever did, but we still call it Bayesian analysis. Another thing that makes it difficult to get your arms around this is that for people like Laplace and Bayes and people of that era, they did not generally recognize the existence of random behavior. In fact, Laplace said very explicitly, if we could measure the position of all the objects in the universe today, we could predict the future of the universe no matter how far out you wanted to look. So they didn't recognize the existence of random behavior. And random behavior is one of the things you have to take into account when you assess measurement uncertainty. It was only 100 years after Laplace that we see the beginnings of what's now called frequentist analysis. And that came from the writing of Ronald Fisher in the early 20th century. Ronald Fisher, in addition to being a superb statistician, was a great hater. And he hated Bayesian analysis. He thought it was sloppy and mumbo-jumbo. He hated the prior distribution. He hated what he called the subjective element. So he and people like him decided to concentrate only on random behavior and develop tools for describing how random behavior worked over time. In fact, that's where the name frequentist comes from. It talks about the frequency of particular random outcomes. Sometimes people call the frequentist approach classical statistics, but how can it be classical when there's a different approach that's over 100 years older than the beginnings of frequentism? I can't explain it. It's kind of nutty. So enough of the problems and enough of the history. Let's talk about two different applications that would support both of these approaches. The first example is a situation where you have to estimate the measurement uncertainty of a system that involves using a die, like this one. I got this online. It was very expensive. It comes with a cert that says the randomness of this die is validated using a die that happens to live in the NIST building. So your die is random. Well, Okay, that's great. But when I've got a die in my hand, the obvious thing that I would do is roll it and study its behavior. And as a matter of fact, frequentists would not recognize the legitimacy of this document because it's not random. It doesn't refer to anything random. It's a statement of validity. So their only choice is to roll this die and study whether it's random or not, and then state where does it fit into the estimate of measurement uncertainty. That's great. You really don't have any other choice, and it makes a lot of sense. However, I can think of another situation with the opposite outcome. Suppose you need to estimate the measurement uncertainty of a system that involves measuring a voltage. You use this meter to make that measurement. You can see from the sticker that it's traceable. You can tell from this distinctive yellow color it's a Fluke meter. Fluke makes some of the best handheld meters available. One thing that's good about them is the superb documentation that comes along with them. Now in this situation, I have the same two choices I had with the die. I can either use the documentation that comes with the Fluke meter to tell me what's this contribution to my overall uncertainty, or I can study it and create my own type A data. To do that, I'd have to purchase a very expensive standard to allow me to compare it to this meter. Then I'd have to assemble the data and add that to my measurement uncertainty statement. That would be crazy, given that I already bought the meter, and when I bought the meter, I bought the certification and information I need to talk about its uncertainty. Why would I go to the expense and the waste of time to study something that I've already got in hand? It would be nuts. So I'm going the type B route, which is the Bayesian approach. I'm going to use someone else's certification. I don't care about the randomness that we cared about in the die. Okay, so we have two different outcomes that are both covered in the gum. If it were true that type A data and type B data never intersected, we'd be cool. We'd use the appropriate method when it was called for, and we'd motor on. It's not that simple. Sometimes both of these approaches can be applied in the same situation to provide an estimate of probability. Lots of times they come up with the same probability. So in those cases, we really don't care if we use the type A approach or the type B approach. It's not that simple either. Sometimes the probabilities produced by these two methods are significantly different. It's actually quite easy to produce a situation where you end up with that contradiction or paradox. I don't have a solution to this. People have been arguing about this for 200 years. Nobody's got a solution to this. So we just have to coexist in this situation and watch out for these paradoxes. I'm really liking making these videos. I intend to make more on the questions that come up when we study the landscape that surrounds us when we try and do an estimate of measurement uncertainty. Now, I've covered a lot in a little less than 10 minutes. I have a wonderful resource if you'd like to learn more about the question of Bayesian versus frequentist statistical inference. Go to YouTube, look up Dr. Kristen Lennox, Lawrence Livermore Labs, and the title of her presentation is all about that Bayes. This is a wonderful presentation, even though it takes 50 minutes. Dr. Lennox is a statistician, so she knows what she's talking about. She's clearly got a lot of teaching background, so she gets her stuff across easily. She's talking to an audience that's quite a bit similar to you guys, and she doesn't have an axe to grind. So she presents everything way back and then brings it forward to the present time, and she speaks clearly. On top of all that, she's got a sense of humor. I've watched this same video at least 6 or 7 times. Every time I do, I get more out of it. I'm really liking making these videos. I hope you'll stick around while I make more. In the meantime, thank you for your attention.
Underneath your pale feet, pour into your lips.